Li from the Chinese University of Hong Kong. And today I'm going to introduce the work from our group, a general and efficient query method for learning to hash. Here, learning to hash refers to the class of important machine learning algorithms developed for similarity search. And I will talk more about this in this talk. Many types of real-world data are represented as high-dimensional vectors, such as those text and images. Similarity search among these vectors foundation many applications, such as recommendation, neural network training, and also the second work presented by Menassi today. And among all the algorithms, hashing-based similarity search is popular due to dimensionality reduction and sublinear query complexity. And learning to hash, which attract more and more attention from machine learning community, is able to adapt the hash function to the underlying data sets and significantly improve the performance. And machine learning community developed many algorithms for learning to, for different types of application scenarios, which include unsupervised hashing, supervised hashing, and so on. Learning to hash has two key operations, projection and quantization. The projection will project a data in high dimensionality to a low dimensional vector of real number. And the quantization will quantize this real number vector into a binary code. The key idea behind learning to hash is that if items they are similar in the original space, they will tend to have similar binary code, which means that they will have smaller Hamming distance. Existing method adopt Hamming ranking in the query processing. The idea is like this. Before querying, I will organize the items with the same binary code into the same bucket. And in this example, we use 2 bits, and the total number of buckets we have is 4. And in the query, a query will probe buckets with smaller Hamming distance first. Like in this example, let's assume the binary code of the query is 0, 0. Then query will probe 0, 0, bucket 0, 0 first because of Hamming distance 0. And these 2 buckets of Hamming distance 1. And the last bucket is 1, 1 because it has the largest Hamming distance 2. But the problem is Hamming distance is cosgram. And it cannot separate buckets of the same Hamming distance. Let's say at this example, for bucket 0, 1 and 1, 0, they both have the same Hamming distance to the query, to the binary code of this query. If we process larger data sets, we tend to use longer code, and there will be plenty of buckets having the same Hamming distance. In this paper, we propose a new distance measure, which is quantization distance. QD take into consideration of absolute project values of a query. Let's assume the absolute project value of this query is 0.2 and 0.1 for 2 bits correspondingly. Then the bucket I will probe will start with bucket 0, 0. The QD is 0 because both bits are the same. We won't consider the absolute project value. And the next bucket we will going to probe is 1, 0. The QD is 0.2. It's because the left bit is different. We sum the absolute project value of the left bit. And the last bucket is 1, 1, which we need to sum both absolute project value because both bits are different. Quantization distance is more fine-grained that it can tell the buckets of the same Hamming distance apart. But the problem is that ranking buckets by their quantization distance is more expensive than Hamming distance. And it normally requires sorting all the buckets. And our solution is generate to probe algorithm. The idea behind is that we will generate the buckets to probe. And these buckets generated are in the ascending order of their QD to the query. And normally, query usually stops after probing a small number of buckets. To generate bucket to probe, we define the concept of flipping vector. A flipping vector is used to flip specific bits of a binary code and generate the bucket to probe. And in this example, I will flip the second bit of the binary code and obtain the next bucket to probe. But the problem is we need to generate buckets in their ascending order of quantization distance to the query. To do that, we need to traverse this flipping vector tree. And this flipping vector tree is generated by two key operations we define, which are swap and append. An important property of this flipping vector tree is that the QD of one node is always smaller than the QD of all its children. And this figure shows the performance of our algorithm. We try our algorithm on PCA hashing, and we can see that the accuracy in terms of precision can be significantly improved because QD is more flagrant than Hamming distance. What about efficiency in terms of overall running time? We can see that after we apply the generate-to-probe algorithm, we can achieve better query efficiency than Hamming ranking and optimize Hamming ranking when we also apply the flipping vector idea to Hamming ranking to get a better algorithm for that. More importantly, our algorithm does not restrict to a specific setting, which means that PCA hashing. Our algorithm also applies to other learning to hash algorithms, such as ITQ. We can see that we made improvements. And consistently, we can also improve the spectral hashing. Here we use ITQ and spectral hashing as an example because they are widely applied in computer vision community. In summary, we propose a new distance measure and develop an algorithm to avoid ranking all the buckets. And GQR, our solution, is able to improve the performance of many learning to hash algorithms and demonstrate its generality and efficiency. And one advantage is that our solution does not bring extra overhead to the learning process, such as deep hashing. All of our source code are open source on GitHub already. We have prepared abundant learning to hash method for you to try. We noted that GQR is part of a bigger system project in our group. And we also developed the distributed version of GQR, which has been released on the LoSA system, which is a general system we developed for similarity search. And you can access all of source code from this SO link or on GitHub with keyword GQR or LoSA. Thank you.
Question? So I have a question. So can your method support any type of data or only some?
Only vectors.
Only a vector?
Yes, real number vectors.
Okay. Thanks for speaking.
Thank you.
So next work is from Hong Kong University.